Thanks for joining. This is Essence of Science. What is time?
I'm Dr. Bossi.
I'm Misha.
So we are going to talk about what is time. And it is not as easy as it looks like. Amanda, what time is it?
4:08, 4:09
But
p.m. CT
where?
in Minnesota.
Yes, because this is as easy as that in New York, the time is not the same as
No,
here.
it's 5.
But even imagine you pick up the phone and talk to somebody in New York or Germany. When you're asking them, what time is it? They will tell you their time, right?
Mm-hmm.
And then you can calculate, yeah, in New York or Germany is that much in front of us and calculate that. But in the moment they say it is 4 o'clock in the morning or whatever it is, like in New York, it is probably 5 o'clock. You call somebody in New York, they say it's 5 o'clock. If they're accurate, by the time they tell you it's 5 o'clock, it's not 5 o'clock anymore. Do you know what that means? Misha, help jump in.
Like
What does that
it's 5, more or less 5, like 3 seconds after 5, right after you
mean?
speak.
3 seconds. No, it is light travels at what speed? 300,000 kilometers or 170,000 miles a second, right?
Yeah.
So if they have a really accurate time, when they tell you what time it is, by the time their voice or image or information get to you, it's already a few nanoseconds later, because that is the time needed for the information get from New York to here. So are you looking at me now?
I'm looking at you like couple nanoseconds before.
Before we imagine when you're driving your car on the street, you're looking forward and you're seeing the cars are coming. Are you looking in the future?
You're looking in the past.
You're always looking the past.
Yeah, and that is actually one of the reasons that I don't really believe in like constellations and like stars.
Oh, like astrology.
Like astrology, because they're so far away from us. Like they're 200 light years away from us, and
no, some of them are hundreds of thousands of light years.
Yeah. So
some of them actually, there are other galaxies that they exist outside of our Milky Way, some of the constellations, and and they are so far away that the light needed millions of years to get to us.
Yeah.
And by the way, many of those constellations, they are just stars in random places that they look in the same plane to you, but one is like hundreds of thousands of light years behind that. Like, imagine that if I'm looking at you on this, it seems that you have a pin on your face.
Yeah.
But truly, you don't have a pin on your face because it's so far away from you. If I change the direction. So, but is that the only reason you don't believe on the constellation?
No, like I have my own theory, and it goes like this. So I was born in 1998. So suppose on the day I was born, I was
born same year.
Yeah.
We're only a couple years apart.
Yeah, like a couple days apart.
Yeah.
Days apart, like 6 days or something.
Yeah, six days, I think. So imagine on the day I was born, the brightest star in the Aquarius, right? In the Aquarius was eaten by some space worm, and it will take us about 200 years for us to realize that it was eaten on the day I was born. So
Eaten? What do you mean eaten?
or like consumed or eaten by a space worm or consumed by a black hole. It's gone.
Yeah. It's space. No, I'm not sure what space worms are.
Well, there's crazy stuff in the universe, I guess. So
I talk about wormholes.
yeah, wormholes or space worms or aliens or Dyson ball. Do you know like a Dyson ball?
What's a Dyson ball?
So like that are an artificial thing that surrounds a star to collect its energy.
Okay.
Yeah.
Actually, that's a Dyson ball. That the level 3 kind of civilization.
Yeah.
Actually, level 1 civilization that consumes the whole light of the its star, yes. So you are born there, that star was destroyed 100,000 years ago, but the light from that star hasn't still gotten to us.
Yeah, so that's what I mean by I don't think that star will have any impact on my life.
What do you think?
What do I think about Misha's theory?
Yeah,
I agree with Misha's theory.
so you don't believe that constellation, that your Scorpion,
Well, we talked about this before and constellation, like it doesn't actually. Well, what we talked about was the seasons and when you're born, like different amounts of light, different amounts of fresh
sweet
air
Lord, you're listening to what I
are gonna
say.
impact
I'm
your.
so proud.
Thank you, thanks. I believe in that part. For you guys who don't know what I'm talking about, you can go back and watch that video.
Yeah. So that's the moral of the story. You are always looking into the past.
Hmm.
You're looking at your hand. The light has to get from your hand to your eyes.
Hmm.
And then that signal in your eye has to travel to your brain, and then register it. So we always, that's just not what we see. What we hear is even much slower than the speed of that sound. Sound is much slower than light actually. That's why you see the thunder, you see the lightning before you hear the thunder. So and that is what the nature of time is. Time is something that shows you the passage. You don't really, it's really hard to know or understand the time itself. What you understand is the passage of time.
Hmm.
Imagine, how do you know what time it is? You just looked at it.
I wouldn't know what time it is if I was in this room because without any clocks, because there's no sun.
But you knew that it's in the afternoon.
Yeah. Based on my day.
Yeah. Imagine you're in the middle of the space, there's no other star, there's nothing there. How do you know the passage of time there if you don't have any watch or anything else? It's almost impossible to understand the passage. You can use your heartbeat, but that's still, you're using changes in some thing to understand the passage of time. Do you know the most crazy thing about that is that actually, some people thought of it, but Einstein, he really put it in together, is that passage of time is not the same for everybody. The passage of time is that actually changes. The same thing that you call a second can be different depending on who is observing it and at what speed they're traveling. Now, I don't know if everybody can really wrap their head around what that really means. How revolutionary that idea is, that the time and space, they're connected in a way that one cannot exist without the other. The same way that if you're suspended in the space without anything, you cannot say what time it is. You as well, space itself without the time becomes irrelevant. I mean, what would that even mean? You are in this room and time doesn't pass as time stands still. That these two have no meaning. Space and time have no meaning without each other. Now, what do you know about the Einstein theory of relativity, Misha?
Not much. I know like E equals mc squared.
Yeah, what does that mean?
I don't know. Like
Yeah,
the energy equals the mass times speed of light squared. I have no idea what that means.
That is actually like, what it truly means is that I could transfer the entire mass of this pen to energy, and that could supply the whole planet for 6 months with energy. Just the mass of the entire planet, everything humanity needs. That meaning that the mass and energy are the same. Mass can become energy, energy can become mass, and so on. But that's not really the big part of the, that's a consequence of relativity theory, but that's not what the relativity theory actually says.
So what does it say?
Amanda, when you are throwing a ball at Lily, imagine while you're throwing the ball at Lily, you're running. So, and then you throw the ball. And if you throw the ball like, so fast that it goes like 10 yards a second, and you are walking or running 5 yards a second, what would be the speed of the ball? You're walking or running 5 yards a second, and you throw the ball at 10 yards a second. So your speed and the speed of the ball, they add together.
Yeah.
And this is common sense, right?
Yeah, yeah.
Or if you walk backward, if you run the opposite way and you throw the ball at 10 yards, if you walk backward 5 miles an hour, you throw the ball at 10, that's subtract, then your ball is all of a sudden slower. Because you're walking backward while you're throwing the ball, they add and subtract from each other. And that's so common sense that we never thought even there's anything beside that is even possible. But imagine, doesn't matter how fast you go, you throw a light, a photon, which is like a small package of something, okay? And then no matter how fast you go, that package of light goes always the same speed. As a matter of fact, if you go really fast, is the space, no, the package goes the same speed. It's the space that becomes contracted, meaning that it's really hard to wrap our head around.
Yeah.
That imagine, if I'm so close to the speed of light that I'm half of the speed of light and throw a photon to that wall.
Can I try looking up an image?
Yeah, do that.
What would be a good keyword?
Well, they just put, Einstein relativity theory.
Einstein Bagels. Have you had that before?
No, what is that?
It's a bagel shop. Yeah, it's pretty good.
Yeah. Bagel shop.
Because there's Einstein Bagel shop, right?
Fun.
Yeah.
Einstein Brothers?
Yeah,
This is what I always think of when I,
yeah, but that's a different kind of.
this is
That is a
gravity.
consequence. Yeah, share screen.
Yeah.
That is you see that there? I know that's a very catchy picture, but that is not the Einstein's theory. That is actually a consequence of Einstein's relativity theory, that a mass actually wraps this, wraps the space around it.
Mm,
Like, we know from Newton that if you throw something in space, it just continues going straight. If nothing acts on that ball, will go for eternity, that ball will go forward. But if you do the same around this Earth, it goes around the Earth. And Isaac Newton was thinking that there is some force from Earth pulling on that ball, holding it there. But now we know there's really nothing there that pulled the ball and the Earth together. But the Earth is so heavy that actually warps or it bends space around it, that the ball is still going to stay a straight line, but that straight line is actually
bent.
bends around the Earth.
Yeah, I remember in school the quote, the dent in time, and the gravity is the dent in time.
Yeah,
The
not
fabric of time.
space-time.
Yeah, yeah.
No, and that is where we are going. What you see there on the right side is that actually, okay, so what you see there is this schematic of Earth bending. This is the 2D, but in reality is a 3D, meaning it doesn't matter from what side you come, the space, the three-dimensional space is bent around the Earth. And obviously it's more around the sun. So Earth going around the sun, but actually in actuality, Earth is going a straight line, which is bent around the sun.
Mm.
Now, let's talk about gravity, because now that we are talking about gravity, not time, but the gravity and time are interconnected. we talked about the history of time, and again, go watch the history of time that we did last time. We talked about atomic clock.
Yes.
Did you remember how atomic clock worked?
Sort of. The cesium particle.
About
And
10 billion
about 10
oscillations.
billion oscillations. I actually have a file from 1967 that clearly defines what 1 second is.
Yeah.
Do you
it's
want me to
nine-
put it up there?
Yeah, let's put it up there. So we know that, if you put that cesium atom, it oscillates so many times a second, and we eventually decided that many oscillation of cesium atom is that it's 1 second.
Yeah, you okay.
No, 1967. Not
Yeah,
that much older than me.
not much older than,
That's crazy how like this type of information really
So
isn't
recent.
that, yeah.
No, it's not.
I
So,
was learning stuff about Einstein last night actually on TikTok. And I was thinking, I can't believe all of this was happening when my grandparents were alive.
yeah, we didn't know most of this stuff long time, even 100 years ago.
And it makes me think about what are we gonna find out
In 100 years
yeah.
from today.
Because I remember one time, and we should do another topic about this eventually, but I asked you, how do we not
Yep.
know, or how do we know that those are all the elements on the periodic table? How do we not know more? Or like, how do we know there's not more when we investigate other planets? I still don't believe that we know all of them.
We will talk about that another time. But
Yep, here you go. The definition of a second.
yeah,
The second is the duration of 9.1 billion like periods of the radiation
Yeah.
correspond.
I rounded up to 10 billion. It just
Yeah. Yep.
sound easier to remember. But now that can be replicated anywhere. Like
Yes.
you can replicate it here, you can replicate it on a different planet. You can just take that cesium atom, give some electromagnetic waves to it and see how it interact and measure how many times it does is reliably
Mhm.
measured. But guess what? This is so accurate because so many oscillation, 10 billion oscillation. You build a clock like that, and you put the first clock, you build two of them. You put one on this table, and you set the other table on an airplane that goes around the Earth, come back. What do you think what those two clocks are going to show you?
What kind of clock are they?
These
Like
are
atomic
Yeah,
clocks.
atomic clock. They're very accurate.
Intuitively, I think they would be the same, but probably
They're
not the case.
The same.
Oh,
The
really?
one that goes faster around the Earth and come back, the one is here. The other one goes around the Earth and come back here. The one that goes faster, it's few nanoseconds behind the one that was on your table. But now I'm going to tell you something that will blow all our minds. Only nerds would appreciate that. And that's why she's laughing. Now, imagine you have two of those clocks. You put one on the ground and you put one up here. The one that's up there, which is farther
Yeah,
away,
against farther.
farther away from the center of
yeah,
gravity,
center of gravity.
goes
It's
faster
gonna-
or slower?
Well, I'm gonna say it's gonna go,
Go
What
faster.
happens in this? What happens in the center of a black hole where there's a lot of gravity
things go so fast that they
and stops?
Yeah. so fast that they stop.
In the
right?
singularity, where the gravity is infinite, time stops. So farther away from center of gravity,
So go
faster your clock goes.
So what will happen if you enter the center of a black hole?
Oh,
Would you
that's
get
a
stretched out?
Yeah.
That is a different, as a matter of fact, you do. It's a process called spaghettification.
Is that a real word?
Yes, this is that.
Spaghetti noodle.
Wow.
So see, when you fall in a black hole, at first there's the event horizon where the gravity is so severe, so much that not even light can escape from.
Mm.
But you don't notice it because for you everything going normal. But eventually you get closer to the singularity, which is the center of the center of the black hole. So that, like, imagine if you're standing the gravity, the weight on your feet is a lot more than the weight on your head. So if it's pulling harder on your feet and on your head, even though you're falling, this put a force on you, make you thinner and thinner. First you become thinner and thinner, then you become a noodle, then your atoms fall apart, then your inside of your atom, your quarks fall apart, and you become a strand of energy. By the time you enter the singularity, there's nothing left of you. You're just a one linear beam of energy. But in that process, it's the point that you look like a spaghetti because you're that thin. And that's called the process of spaghettification.
I think it's cute that these people that come up with these terms have a little bit of a sense of humor.
You know what happened to the person though, right?
What?
For a long time, you know, in the Middle Ages, they would put somebody on a
Yeah,
Or
and stretch them out
stretch them out.
for torture.
Yeah. This is the ultimate stretching.
Yeah.
A person first become very thin, very long, then become like a strand of spaghetti, and then become a beam of singular atoms, and then the elementary particles before it's hit the ground. But by that time, guess what? For them, time stops. There's no time for them. There is like, I don't know how anybody can wrap that around their head that, you know, the time stopped existing. Let me tell you another story. What's the closest star to us, Misha?
The sun?
Yes. After that,
I don't know.
Alpha Centauri.
Oh,
Is that the North Star?
No, it is not. Good try though.
Thank you.
So it is called Alpha Centauri, which is we thought is one star. Then we found out there are two stars. Now we know there are three stars. There are two, one big one, one smaller one, one like a red dwarf or something. This is about 4.5 light years away from us, meaning that when we look at Alpha Centauri, we are looking actually 4.5 years in the past. So the light takes 4.5 years to come from Alpha Centauri to us. Imagine you are now a beam of light, a photon of light. You are traveling at the speed of light. How much time does it pass for you for the light? How much the time the light is created right now? It's happy, just born, and gets shot down to Earth, coming toward us. And then, oh, it's in our eye or in our telescope. How much time has it passed for that light, for that photon?
wow. Intuitively, I would say like 4.5 years because that's what it's on in reality. Maybe zero, not zero.
That 8 minutes takes for the light from
Sun
Yeah,
to,
right.
but we're talking about the 4.5 light years, that star, right?
that the Alpha
Alpha
Centauri.
Centauri.
I come back to that. That's very interesting thing. I will come back to that. No, even though for us it took 4.5 years for that light to come to us, that photon, because it travels at the speed of light, it has no time perception. For that beam of light, for that photon, he's on the way to Earth, and boom, right there. Not even like this. It's created and it's right under our eyes. Photons do not perceive any passage of time. For them, time does not exist because they're traveling at speed of light. The same way that, you know, if you have the two of you and I send you one around the, you know, with the, almost like it's something that has 90% of the speed of light, when you come back, she and I are grandmas and, you know, we are barely able to walk. And for you, it has just few days has passed. When you are very fast, time passage is very slow for you. But if you're truly at the speed of light, the time stops. As a matter of fact, nothing can really, no matter, nothing that has mass can travel at the speed of light. Why not?
There's
Why
not.
nothing that can, why nothing that has a mass can travel at the speed of light?
Mm, I don't know. Let me think. Do you have a hint
Yeah,
from Einstein's equation?
so the hint is that imagine when you are getting faster and faster, imagine that every time you are getting faster, you're actually getting accumulating energy, right?
Mm,
Every time you accumulate energy, you're getting heavier. Can you imagine that? That actually when you travel faster, you become heavier. Because energy and mass are convertible. We just did
yeah, yeah, yeah.
meaning that something that travels faster, the energy of the traveling faster make them heavier. And the equation is very easy. Every time you get closer to the speed of light, you need more energy to accelerate even more.
Mm,
To a point that when you get so close to the speed of light, your mass becomes infinity. That's why nothing that travels, nothing that has mass can can reach the speed of light. That means, as well as a consequence, meaning that for us with mass, time never stops. For the photon, time has no meaning because photon has no mass.
Mm.
Okay, so now let's talk about that. You have the atomic clock, you put it down close to the center of gravity, it becomes slower. You send it higher up, it becomes faster. You send it on a trip, it becomes slower. You make it stop moving, it becomes faster. And the idea there is that, imagine that we are traveling in space-time. Like when I tell you, let's say, let's go to Costco. I'm telling you where to go, but does it have any meaning? Because you might be in Costco today and I'll be in tomorrow.
Or different Costco.
Or different Costco, but when I say let's meet in Costco in Burnsville, I'm giving you a 3D coordinate in the space. I'm telling you where that is. The Costco in Burnsville has a specific address, but then I have to give you as well a time. Tomorrow, 4 p.m. You understand if I say 4 p.m., it means 4 p.m. Standard Central. So try to identify any event without that. It becomes meaningless. So for every event to happen, you have to have a time and a space coordinate. And that is how any event in the physics is defined, with the time and with space. Now, something like this thing here, let's say we are static, nothing is moving. It's not moving in space. The whole motion of this will be in time. But when I'm moving it in the space, some of that motion in the space get transferred to the time, meaning this, when I'm moving this, the space becomes shorter to the time. And literally, that's what it is. When you travel faster, the space contracts. It's very hard concept to really to understand.
Space contracts like a wormhole?
Well, wormholes are a
No,
little
they're different, right? Yeah, but
theoretical. We don't really know if they
Yeah.
exist or not, but the construct that connect two space-time locality with each other, meaning that imagine that a sheet of paper.
yeah, and you fold it and
A
you
sheet of paper that to go from here to here, you have to kind of go there, and that will always take time. But now imagine that if you fold that and connect them together, you can go from one to another without really going through a regular space.
So it's a fold in space and time?
You can say that, yeah, it's a shortcut fold between the space-time.
it's three-dimensional, so it's more like a sphere, right?
Yeah, it is a sphere, it must be a sphere, but again, that's a very quick, it's a consequence of Einstein's relativity theory, we haven't found any yet, but it is a consequence of that. But that means that, you're traveling in time and space, the two ends of the wormhole, they don't have to be in the same time. They can be like, one is today here, the other one is 1,000 years in the past or future, but it's more theoretical. So coming back, what is time? All of a sudden, you're more confused now than we were when we started this, aren't we?
Yeah.
A little.
And so are the physicists. So are the physicists. So are the biggest mind on the planet who deal with that. More you look into that, the more confused you will be about what is the nature of time. Like, what does it mean that we are getting older? For the biologic aging, we have a definition. Your body becomes less can regenerate less. You literally
You become slower when you're older.
yeah.
More
This is a
pain.
biological time that we understand, that all of us understand that. But when we get to the actual nature of what time is, I think that our intellect really fails us to truly understand what time is now. But there's lots of phenomenon around the time that it makes us really understand that how complex and how confusing this is. Like, imagine there is a so-called space, like a space-time cone or light cone. That is a little bit of a complex thing, and maybe we save it the most of it for a different time. But it says that if you have like create a light here, and the speed of light is practically the maximum speed that information can travel.
Yes.
That's exactly what it is, meaning that nothing can travel faster than the speed of, no information can travel faster than the speed of light. And if I bump this pen, dump this, obviously I'm far, far below the speed of light, so I can interact with this pen, this keyboard. See, this keyboard move, because this pen moved that keyboard. Now, when we get to higher speed, like I can send the beam of light from here to moon or somewhere else, that beam of light with the speed of light can activate like a switch or something. So I can truly change something on the moon with the beam of light. Okay. Now imagine that beam of light going to somewhere far, far away, like Alpha Centauri, 4.5 years. As soon as I can make any changes on Alpha Centauri, is 4.5 years. That as soon as I can make any change, convey any information, send them a message or anything on Alpha Centauri. Now, there is something extremely, even more confusing there. Have you heard about the expansion of the universe?
Yes.
Is the name Edward Hubble? Something that you
Yeah.
Yeah, it's also.
The telescope, exactly. What we know about the Edward Hubble and the telescope.
That's what I know about.
In 1930s and so on, he looked at the different galaxies. First of all, he recognized many of those small, fuzzy things that we see in the sky. They are not stars. They are actually galaxies outside of our galaxy. And then he analyzed the light of
Redshift.
those redshift. Yeah. Redshift is practically a characteristic of the light because the light is made of atom exciting and then sending the energy, hydrogen atom.
Mm.
They have a signal. And you can see that signal is stretched, meaning that that star is, or that galaxy is moving away from us, or it's compressed. That means like a Doppler effect. They're coming toward us. He noticed every single galaxy in the universe, except our local cluster, is moving away from us. And further away from us, faster they are moving away from us. Meaning that there are some galaxies that we won't see because they are moving so far faster than the speed of light away from us. We said information cannot travel faster than the speed of light, but space itself can expand faster than the speed of light. So there are galaxies that they are moving so fast away from us, their light will never reach us. We will never see them.
Mm.
And that makes a so-called light cone, meaning that in our observable universe, there is an area that our light can travel fast enough that we can have a meaningful interaction in any way here. But there are certain areas of the space that we can have never meaningful interaction. So they are always outside of our scope of influence. And that's what the light cone means. Anything inside of the cone, we can have interaction. Anything outside of our cone, we cannot have an interaction with. Okay? And it becomes very interesting. In the observable universe that we can look, in our light cone, imagine our light cone is like a loaf of bread. You can cut the loaf of bread in different directions. What it means, I'm just going to tell you the interpretation of that. Meaning that my now is not somebody else's in the other side of the universe, is not there now. For us, for three of us, our time or now is now because we're too close to each other. But it becomes based on calculation. This is a fact. If I'm looking at the other side of the universe, and if I'm driving with a bicycle, just a bicycle, speed of a bicycle, but I'm looking at the light that's coming from a galaxy that's, let's say, 7-10 billion years away from us, I'm seeing 40 years. No, obviously, I'm looking into 10 billion years in the past. But if I'm driving in the direction of that galaxy, I'm looking into 10 billion and 40 years. If I'm driving away from that galaxy, I'm looking into 10 billions minus 40 years.
Wow.
This is unbelievable, meaning that I can look into a galaxy within almost like 80 years, like a century, back and forth, depending on if I'm going toward that galaxy or away from that galaxy. Now, 800 years, 80 years, 40 years is really nothing, because this is 40, like it's 7-10 billion years ago. But just the concept that if you calculate that any concept of time that we realize in our daily life becomes almost so meaningless, so comically, absurd when you look at the physical world, what the time really is. Now, I am sure both of you and almost anybody who listen to us is not less confused about time, or more confused, but that is exactly, I think the value of this podcast today is that thing that you are looking at right now is not as simple as you think it is, and the concepts of physics that they make your life, they are so multifaceted, they are not straightforward.
Well, yeah, I feel less upset about my delayed delivery.
I want to put a cherry on top. You said something about 8 minutes.
Yeah.
Amanda, what was that?
Time that it takes the light from the sun to hit us.
Okay, now let me give you a trivia. Photon is, where is the light generated in the sun?
On its surface?
Is it?
I don't know.
Where does the nuclear, thermonuclear, the fission, how does the light is produced in sun?
Nuclear fission? Fusion.
Fusion,
It's
yeah.
fusion.
Two hydrogen atoms come together. Actually, 4 hydrogen atoms come together, they make a helium atom.
Yes.
The helium atom is a fraction less heavy than the 4 hydrogen, and the difference becomes energy in the form of light, correct?
Mhm.
So that fusion reaction, where does that fusion reaction happen?
In the core? In the core.
Now the surface, right?
Mm.
Okay, so the light is created in the very middle of the sun because the pressure and temperature is high enough to bring those elementary particles together and make a fusion happen. What's the diameter of sun? About 1 billion kilometers, about.
Okay.
Oh my, billion mile kilometer, whatever, around that. That light has to get to the surface to be able to come to us, right?
Yeah.
Even better, what is the distance between sun and earth?
8 light minutes.
8 light minutes, but about 100 billion kilometers. So between earth and sun, you can put 100 sun, but that's it. I would have thought it's much more, but that's what they know, because the diameter of the sun is about 1 billion kilometers and or a mile, I forgot which one. And you can put only 100 suns between earth and sun. So the sunlight gets in 8 minutes from sun to earth. How long does it take for that light from the core of the sun get to the surface?
The surface of the sun,
Yes.
like a little bit over a minute.
Like 8 minutes divided by 100.
You would think so.
Yeah.
300,000 years.
What?
Yes,
Wow.
Why?
Because it's so hot.
it has actually something to do with being hot and dense. Because the light from surface of the sun comes with no interaction with anything, comes directly to us. But what does have the sun, the light in the core of the sun do to get to the surface? It hits to one hot thing and then bounces back and forth, zigzag and so on. It's a calculation actually, it takes 300,000 years. So the sun, the light that you see now, left the sun 8 minutes ago, but was created in the core of the sun when when we barely start having a government in the United States.
So if the sun exploded today, right now, would it take 8 minutes for us to find out?
Yeah.
Okay,
But you'll find out. It's pretty obvious.
in 8 minutes.
It's gonna be pretty obvious.
Fair.
Yeah.
Nothing going to happen in 8 minutes.
But then everything will happen.
You won't feel anything.
Yeah, exactly. To us, it would basically be nothing because we would be nothing.
Within a second, everything is vaporized.
Yeah.
And that actually will happen eventually.
Yeah, the expansion of sun into something, a red giant.
Yeah, very good, said Misha.
Uh,
So what is going to happen when, no, first of all, is sun getting hotter or colder?
colder, right? Is it? Because the
I'm
fusion
looking
will
at-
stop. Because fusion will stop something.
See, how old is the sun? 4.5 billion years. Okay,
Really? 4.5 billion years? I thought that's Earth age.
Earth and sun, Earth was created about few 100 million years after.
Oh,
They're
we're the
almost
same age.
yeah,
Oh,
almost.
okay.
So, now sun is was created 4.5 billion years ago. The core of the sun, was it then hotter or colder?
Colder.
That's what I'm going with too.
Yes, colder.
Colder.
Why?
Because it's just started, right?
No,
So
it's
heating
not.
up.
Still heating up.
Like,
That is a good way to think about it. But no, see, when sun started to create energy,
Mm,
there was so much hydrogen and very little helium. And then what's holding sun together is fission, fusion inside, and gravity from outside. Gravity is bringing things in, and the heat from inside expanding. Then when hydrogen becomes less and less, it produces less fusion. So gravity starts winning. When gravity wins, push it together, it becomes hotter.
Mm.
When it becomes hotter, then other atoms beyond hydrogen start to fuse, like helium or lithium and so on. They start other atoms. So when hydrogen that is more abundant and easier to fuse become less abundant, the gravity becomes more strong, more dominant, and it pushes it together, and then it becomes hotter and hotter and hotter. So in a billion years, sun will become so hot that no life on Earth will be even possible.
Mm.
But then 3 billion years after that, once it's really running out of its energy, the core condenses, but outer layers
Expand.
they expand. As a matter of fact, they expand beyond the orbit of Earth. So in about 3 billion years, our beautiful Earth, our history and so on, will not exist. What do you feel about that?
I feel like it's gonna be even sooner than that like our history doesn't exist. I feel like I don't really want to get really political into it, but we're kind of speeding up the process of our things not existing, our life.
I am also optimistic about that. See, everything you see, this room, this paint, this wall, this table, our intellect, truly has happened in the last few thousand years. As a matter of fact, our technology is just 100 years old in that level. We got 100 years old. Imagine what are we going to be able to do in a billion years or million years?
Or even
100 years, see how far we have come.
Yeah.
We are just talking about
Yeah.
that. In 1,000 years, in 100,000 years, in a million years. That is truly going to be able to do miraculous things.
Yeah, I agree. I think we will be able to do more.
We will, push the sun away or push the earth away. We will be able to do. I'm so much more optimistic about that. Our ability is going to be so far.
But
Yeah.
everything has a consequence. Pushing the sun away from us will have a consequence on other things. Or pushing the sun closer to us will have a consequence on other things. I'm not worried about pushing the sun away. I'm worried about having people get to the point of being able to push the sun away.
So you're concerned about, are we going to go this thing before we achieve that level of technology
Yeah.
that will save us in the future? You're right about it. You have a point there. But you see, you're having this beautiful Christmas dress on because you have something to live for. You're optimistic.
I am optimistic.
So I think I truly believe in human intellect that it has been always the fight between the human knowledge and truly human wisdom. Sometimes we achieve technology and knowledge before we are wise enough to know how to use it. Like, we know how to make gunpowder and then we kill more people. We know how to
Make a nuclear weapon.
we know how to capture the power of the fusion or fission, but then we put it to create a nuclear weapon. So there are lots of examples of that, but at the end, I believe it's a race between the human intellect, technology, and wisdom. But I do believe that wisdom will win. So I think we will be able to muzzle our ambitions.
Yeah,
No,
it'll be Darwinism, kind of like,
no, I hope not.
yeah, the people that aren't willing to adapt.
But well, we just don't want to make sure that those people who don't want to acquire the wisdom don't take everybody else down. But this is coming off from topic
Of time.
for this time. So I think it's time for us to just wrap it up. And we talked about so many different things, but I'm hoping that you understand that we are presenting you a lots of different things that in one area, this like that, we talk about that, that method of education, which is we call that from Finland, Finnish education, that we talk about something, we talk about multiple things that has some connection to our topic, but we tell a story. That story, I hope, stick with you much better than if you just write a formula on the wall and so on. So for Essence of Science, I'm Dr. Abbasi.
Amanda Armadas.
This is Misha. Thank you all for joining with us.
Thank you.